So before we get started actually doing regression, it's always a good idea to kind of examine the data that you have to begin with. So the first thing we'll do is we'll go ahead and get our sample size. So we have a total of 880 skeletons that have been measured for those 8 different bones. And then what we'll go ahead and do is just pull out the y variables, the left bones, and the x variables, the right side bones. So this is saying to delete bones in columns 2, 4, 6, and 8. So that way we get our response variables, and the next line says to keep them since it doesn't have the minus sign there. And then we'll go ahead and get our number of response variables. We'll get our number of explanatory variables, and we're going to add this one here because we're going to have an intercept, that beta 0. So we're going to go ahead and include it with q as well. And then let's go ahead and look at kind of the correlations for everything to try to see how correlated our response variables are with our explanatory, our response variables are with one another, and our explanatory variables are with one another. The problem is it's an 8 by 8 matrix. It's kind of hard to read. So what you can do is let's just go ahead and look at the correlation just for our response variables, the left side bones. We can see that they're all fairly correlated with one another. The weakest one is at 0.87, and everything else is hovering right around 0.9. So all of the bones on the left side of the body are strongly correlated with one another, which can cause issues later on once we get to multivariate regression. If we do the same thing for the right side bones, and we kind of see the same general pattern. Really strong correlations, most of them around 0.9. This time the weakest one's around 0.85. And if you have strongly correlated explanatory variables, that'll cause some weird things to happen later on. And we'll look at that when the time comes as well. And then the last one, if we want to try to make a prediction for how long someone's left side bones are, based off the bones on the right side, let's look how strongly correlated those two are. And again, all of these are fairly strong. The weakest one is about 0.84, and most of them hovering around 0.9 or higher. So all of our variables, both left side, right side, and with each other, are all pretty strongly correlated, which is good. You want your response variables to be correlated with your explanatory variables, but having explanatory variables that are correlated, generally pretty bad. Having response variables that are correlated, also pretty bad. And we'll see why when we get to our inference methods and our estimation methods. So we'll start off with the easier version of the two. We just have one response variable and multiple explanatory variables. So we can write out our model for multiple regression in our linear algebra form. So we just have one response variable, and we're going to have n copies, or n observations of that response variable. So if we're just looking at the humerus, the left side, instead of looking at all 4, we'd have 880 measurements of just the left humerus. And then we're going to have this X matrix, which is the same one that we kind of saw in the previous video. It's going to have all 4 right side bones in it. So we'll have 4 columns for the slopes, plus an additional one for the intercept. So this is actually going to be a Q+1 matrix for our 4 bones, and we also need to include an intercept for every single observation that we have. And then what we want to try to do is we want to try to see how much y changes as these explanatory variables change. So for the first explanatory variable, it gets its own slope, and we'll multiply those two together. For the second explanatory variable, it gets its own slope, multiply those two together. So you want to remember that linear algebra, how you multiply matrices is you take the first row, multiply it by the column, and so essentially we're turning this into just another vector. And again, x times beta will hopefully be pretty close to our response variable y, but every person's unique. They'll all be a little bit different. So we're going to add in our error terms, kind of how much each person varies from the expected amount according to our linear model. And anything in statistics is going to have some sort of assumptions. And our assumptions, in order for this model to be appropriate for our response variable, is we want our errors to be 0, essentially saying that our model is unbiased. We're not leaving anything important out. And so what that essentially means is that while all the response variables are going to be different than what we get here, on average, we should expect to get what the model tells us. And then the second assumption is that essentially all of the response variables have the same variance, sigma squared, and they're all uncorrelated with one another. That y1, y2, all the way down to yn aren't associated in any way. They're kind of new independent samples from one another. So that way there's no kind of overlapping information across the rows, that all of our samples are independent from one another. So those are our two big assumptions when we're doing any kind of regression. So kind of the way I tend to visualize these things is we have a vector that we're going to store our response variables in. So this is our y vector. And we're going to say that's going to be equal to this big square that's going to have the same length as our response variable, but it's going to be q plus 1y. The q for our different q explanatory variables x, and then that 1 for the intercept that we always have. So we're going to have this big block that stores our explanatory variables, and then we're going to use this vector beta to transform them from x into y. So this is also going to have width 1, just like y does, but it's only going to have length of the width of the x matrix. So it has width of y and the length of x. And then we're going to add in our error terms. So these two will be the same dimensions, 1 by n. And then this is going to, we need these two to be conformable so that when we multiply these two together, go row by row by row all the way down, we end up with the same length or the same size as these two matrices here. So how do we go about estimating or trying to figure out what this beta vector is? So we know y, we know x. What we're missing is beta and sigma. So we want to try to find estimates for those. So what we want to try to do, and kind of the goal of linear regression, is we want our prediction for y to be as close to the real thing as possible. We want our predictions to be close to what we observe. So we're going to try to minimize these errors. We want to make those as small as possible. So we said that we expect these errors to be 0, so if we just average them out, they'll end up being 0. So what we need to do instead is, because some of these errors will be negative, some of these errors will be positive, what we'll do is we'll just square them all. So that way everything's positive. So if we kind of solve this up here for sigma, or epsilon, we can move this over here and we get y minus x beta. And we're trying to estimate what beta is. So anytime in statistics we're estimating a parameter, we'll just put a little hat on top of it to indicate this is our estimated beta. So that's E, that's our error term here, our error term here. We square them by multiplying them all together and then adding them up. And that'll give us what we refer to as our sum of squares error. You've probably heard that term before in other statistics classes. So essentially all we did was we took y, subtracted out our prediction for it. For each one of those, we squared all of them. That's kind of what this line is doing. If these weren't matrices, if these were just scalars, where this was a single y and this was a single x and a single beta, then essentially we have e squared. And then if we turn them into vectors, essentially we're just kind of adding them all up at the same time. A vector times a vector gives you a scalar, and it's going to be the sum of all of our residuals squared. So we want to try to figure out what value beta hat needs to be in order to make this the smallest. And skipping some vector calculus, what we end up getting is that beta hat is going to be equal to our x matrix transpose times x inverse. So we're going to take the inverse of this product of our matrices, x transpose y. And this is what we're going to use for pretty much every sort of linear model you've ever seen in statistics. That's kind of where our estimates for our intercepts and our slopes come from. And so we talked about at the beginning of this video that if x's are highly correlated, what that's going to do is it makes kind of this what we refer to as unstable. Because the more and more correlated the x variables are, the closer and closer to being singular this x transpose x matrix becomes. So if two columns are perfectly correlated with one another, if you have two x variables that are perfectly identical, then what's going to end up happening is that you can't actually invert this. And what that means is then you can't estimate what beta is at all. So what that's going to cause is it's going to make our estimates for beta kind of unreliable if there's not perfect correlation, but if there's close to perfect correlation. And we saw that our x variables were pretty strongly related to one another. And that can cause issues later on, and we'll see what happens when we get to it in the R code. So we found a way of estimating beta. Also, we now want to try to find a way of estimating epsilon. So we have our equation for estimating y is all we'll do is we'll drop this epsilon, and then we'll have y hat is going to be equal to x times beta, our explanatory variables times our slopes. That'll give us what our estimated y is. And again, this y hat is not going to be the same thing as y. It's just going to be our best estimate or our best prediction for it. And well, we found what our estimate for beta hat is. So if we plug in our estimate for beta hat, this is where our y hats come from. We take the original y, multiply it by this matrix, and we end up basically just taking y and putting a little hat on it. And so this matrix is referred to as the hat matrix, because all it does is if you take this matrix, multiply it by y, puts a little hat on it. So people thought it was cute to call it a hat matrix. And so we want to try to estimate what sigma squared is, because we said that these error terms have variance sigma squared. So what is the error? What is the estimate of sigma squared? So sigma squared, our estimate for is just going to be s squared, and it's going to be the standard deviation, or the variances, of the error terms, or the variances of our residuals. So we summed up the squares of all our residuals earlier, our SSE, and then we just need to divide by its degrees of freedom. And generally, the way degrees of freedoms work is what we'll do is we start off with our total sample size, n, that's the number of observations that we have, and then we're going to subtract 1 for each parameter that we had to estimate. So this beta has q plus 1 parameters in it, and we don't know any of them. So we have to estimate the intercept, and we have to estimate all q slopes. So since we start off with n, we have to estimate q plus 1 parameters, we lose q plus 1 degrees of freedom. So that's going to kind of be our degrees of freedom for sigma squared. And that gives us kind of our estimate for what s squared is. How much those y values, our single response variable, tend to deviate from this line that we're drawing through them. If the response variable is really close to our prediction line that we're creating, if x times beta gives us something really, really close to y, then this s squared will be small. If there's not that strong of a relationship between x and y, then this s squared will be really large, and those our predictions will be pretty far off. So for just multivariable regression, we can kind of calculate this s squared and see how close our predictions are, how reliable they are with trying to estimate the y variable we're interested in. And so this will end up having length n, which is why we have our n down here, that has length q plus 1, and we end up subtracting them out because that's what we have to estimate. So how can we do this in R? So fortunately, we don't actually have to do most of that at all. We can just use this LM function in R. So we'll call model 1 because it's our simpler model. If you use LM in R, that stands for a linear model, we'll put in the typical formula that we usually see. So we're going to just be looking at the humerus versus all the right side bones. So we'll say the left humerus length is going to be equal to the right humerus, right radius, right femur, right tibia. We want to tell it where those variables are stored. They're in the data set bones. And then this little semicolon here says run that code, and then also run the one that comes right after it. If you just run this by itself, it doesn't really give you anything all that particularly useful. It just goes ahead and gives you your coefficients. So this would be our estimates of beta hat. But when we want to start doing inferences, this summary command is going to give us a better look at our model. So it gives us those same estimates that we had earlier just by running this, and it's going to give us the information that we need for our inferences later on. So that's kind of how you can go ahead and fit a linear model in R pretty simply.